Welcome to SOH, the best office hours ever, because you are part of it. This is 2023, Calculus BC, question number 2. Let's see what's about. Maybe you want to solve it in 1 or 2 minutes and come back to see the detailed solution, or you want to stay to see how some of these questions are solved in more detail. So we have a particle that is moving along a curve that is shown here down. Okay, cool. And it turns out that x of t is not explicitly given, but y of t is explicitly given, and the derivative is also given. If we would like to say, oh, maybe, we have that this is the integral of this, right? That's true, but we cannot solve it because it's only numerically. It's not one of those integrals that have an analytical expression. Okay, and then it also tells us that so this means that x equals to 1 and y equal to 0 at t equal to 0. Maybe we'll use that later. Also notice that there are no units, which is a little bit surprising because this is about physics, right? We have a particle is moving, we have a curve, there will be speeds and so on and so forth. But anyway, there are no units. So bear that in mind, especially for the case that there are units in another problem. First question, acceleration vector. So vector is something kind of new. So we have here like ax and ay, we will have two components, and then you have to figure out how to compute each component. Of course, this is going to be related with the x position somehow, so remember this formula to try to solve it, and this is going to be related with the y position, okay? So also try to use this formula. You can also remember that this means another derivative after the first derivative, so yeah, this may help you a little bit more. Okay, so that's some formulas that you need to know. What else? B, find the first time that the speed of the particle, but we don't have the speed of the particle because the speed of the particle has two components, right? Vx and Vy. And Vx is given here, yes, but Vy is not given. So you will have to compute Vy and then build up, this will be the vector velocity, then compute the square root and make it equal to 1.5. Unfortunately, this graph doesn't help very much. We don't know, whether if it's time equal to 1 is here or here or here or here. So it doesn't help very much. But anyway, that's how it is. So this you will need a scientific calculator for sure. Then this one says finds the slope of the line tangent to the path at time equal to 1. Again, we don't know where we are here, so it could be here, it could be here, it could be here. So that's not very helpful. But the slope of the line is going to be dy divided by dt, by dx, sorry, by dx, right? Is the y and x, that's the path. So it's rise divided by run, but we don't have that. We don't have this function, right? Or an implicit relationship. So you have to think about this like this, okay? And then try to solve it. Remember always to use radian mode in all these exams. Radian mode, okay? Radian mode, and all this. Because it's very easy to forget about that, and then you get, this graph doesn't help at all, so you get any answer. Ooh, everything is good, and that's it. But there are two questions here. Find the x-coordinate, only the x-coordinate of the particle at t equal to 1. It's kind of two questions in one. It's like, asking for apples and oranges. Okay, yeah, everything is fruit, and yeah, all may be yummy, but, it has nothing to do one with the other. So be careful with that. You need to find the position at x equals to 1. So it's going to be related with the derivative of x with time, which is here. So you will not use the slope of the line tangent for anything. I will use it as an additional bonus to show you, the approximate solution and how it's related. But if you try to use the approximate solution, which I think it will be very clever, because it's kind of, if you tell me to do A and then B, I will use A in the same question. That's not the official solution. So I don't know. These questions are reviewed by many people, including college professors. So I don't know why they didn't change this. That's not a good wording. And then D, find the total distance traveled. Okay, this is important. Total distance. It's not the position, it's the distance. So you need the absolute value of the speed. Now, whenever you use the square root, you will have to use it because we will define here the speed ourselves. Calculators always use the plus sign. So you can write the absolute value just to be consistent, but don't worry when you do the calculations or add it. It's not going to change anything. And then be careful because this is between 0 and pi, so there are different times it's not equal to 1. So always if the limits change from question to question, update that in your calculator. Okay, that's it. So you can try to solve it yourself and come back with that 5+. or just stay and see how we solve each of them. So let's go for the first question. So we have to find the acceleration vector, right? So that's the key word here, vector. So the acceleration has two components, 1 and 2, and remember that the general definition for the acceleration is the second time derivative of each of the components. That's true, that's just by definition. And in practice, this means another derivative. So in this case, what we have is this one here, right? And chain rule. So you have this and then the derivative of that. And you can write it whichever way you like. You can put the sign before, doesn't really matter. Okay, and then for this one, again, we are going to take a second derivative. So we need to first take one derivative. And this is going to be 2 times cosine of t, because we have this as the function, and then minus 2 sine of t. So basically you have the acceleration vector, which, I mean, if you really want to write the general expression, it's going to be this. There is a common minus sign. I don't know. It's not bad to put it outside, but honestly, since we have to do kind of numerical calculations, I just leave it inside. And then what is the acceleration in t equal to 1? Well, because it's going to be minus sine of 1 equals sine of 1. At least write this. This is very good. And you have it. This is correct. Now, if you want to approximate this in the calculator, use the radian mode. Okay, super important, because otherwise we are cooked. Okay, so how much is that? Well, in the calculator it shows minus 1.444, and the other guy is minus 1.6829. But if we use the 3-digit rule, 3-digit after period, this becomes minus 1.44 and minus 1.683. And notice that there are no units. Okay, there are no units. Anything else? No. I think this is great. We passed it. Okay, what happens next? Find the first time that the speed. Okay, first time that the speed. Well, the first thing to do is to build up the speed function. Okay, we don't have it. But the speed function, the same as we had the definition of the accelerations, this is the definition of the speed. So we need to compute how much is Vx and Vy. Why? Because we want a 5. So Vx is dx divided by dt, and that is given in the problem, in the wording, by dy divided by, I mean, the derivative of y with respect to t. That one is, we have it here, 2 cosine of t. So let's write all this monster here, cosine of t squared plus 2 cosine of t squared, and we want this to be 1.5. And find the first time. Of course, this is a transcendental equation. And we cannot solve it with our standard methods, even if you try to do the square and rearrange things. That's nice. And it maybe simplify some numerical calculations or approximations. But right now, we are just going to use Desmos or your graphing calculator, and that's it. So let's see, because we don't need to remember this by memory. So we want to solve this equation. Now, in Desmos, if you want to solve this equation, you have to write t as an x. You can also use y, but you cannot use t. If you want to use t, what you can do is to do this function, minus 1.5, and find where it's 0. So either way, option 1 or option 2, both of them work. It's up to you. What do we have to do next? Let's see. Next, we have to find the slope of the line tangent, but that's kind of, it's not related with the speed directly. And the x coordinate, no, we don't use the speed. And then finally, the total distance, here we will use the speed. So if we write this with, this function, it may help us later on. So yeah, okay, let's choose this way, because we will use that two questions later. Okay, but otherwise you can change all the t's by x. Okay, let's write that thingy. So the first thing is to write the function, and I'm going to write it as a function of t, because I like t. It's here, and then it's kind of the same thing. So don't forget, don't worry about these sliders. You say y, it goes away. Now square root is here, and now what's a bit tricky is that there are many parentheses and squares. So personally, when I do this, you can see that there is showing that it wants to close the parentheses. Then close it already and add the square here, okay? And then go back inside, and in this way you make sure that you don't forget any parentheses properly closed. So it's e to the power of, let's see, e to the power of cosine of t. So I prefer to write cosine, even though I know there is a function, because it saves me one more annoying parenthesis that they add. And then here we have to get it down, it's up, here it's down, plus and then again parentheses, and we close it. We do the square, and then we go inside. This way, for sure, we don't mess up with anything. Then 2 times the cosine, and as I say, I know that there is a function, but here in Desmos, but I prefer to do this instead of what? Let me go back. Instead of going here and click functions, no, because then that's another parenthesis. So bam, 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 bam. It's pretty annoying. Other than that, yeah, Desmos is great. Then minus 1.5, right? We don't want to do that. We want to do minus 1.5. We chose this option, not 15. Sorry, 1.5. And then, well, beautiful graph. We have to find something. We remember between 0 and pi. So 0 and 3 point something. Yeah, we're getting. This is the first one, right? First one. Now, how many digits? 3 digits, right? After the period. So you just need to zoom in until you find something with here 3 digits. 2.54. It does not reach. So okay, perfect. So t equals 2.254. No units, 3 digits. Done. Fantastic. Okay. The following one is find the slope of the line tangent and then find the x-coordinate. So 2 questions. The slope of the line tangent is this thing. And we don't have that. We don't have either implicitly or explicitly a relationship between y and x. But you can do a division. You can divide each of them by dt. And then this is basically this derivative, so 2 cosine of t, and this is given in the wording, so e to the power of cosine of t. Now, for so the slope at t equal to 1 is going to be equal to 2 cosine of 1 and e to the cosine of 1. Again, very careful with the radians here. So you can write that here, of course, in Desmos or a simple calculator, and that's it. I don't know. Let's do it in Desmos. So that would be like 2 cosine. Maybe here we use functions just to change a little bit. Cosine of 1. But what's the tricky part? Remember, go here and check that you have radians. Okay, now let's continue. Divided by e to the power. It's a pity that they didn't add here e because this happens so often, right? E to the power of cosine. Let's go to functions. So you see, I know that there is a function, but you see this parenthesis. Anyway, 0. This is approximately 3 digits. 0.629630, right? And that's it. Okay. And it's positive. Okay, cool. So we don't know where t equal to 1 is in this graph. You know, this graph here. We don't know where it is in t equal to 1. But if it's positive, it should be somewhere here. One comment is about this graph that we haven't been able to use very much. So let me erase a little bit of it here that I added. It's for the acceleration. That's the only thing that it could have been a bit helpful. You remember that the acceleration that we had was negative here, remember? You can see that when the second derivative is negative, it means that you have a maximum. That's this shape. So the acceleration is always pointing, you know, like. But anyway, it's not super helpful still. Yeah, you can see how the ax is going to be always negative, and ay, well, it's a little bit more confusing. Okay, but you have these vectors pointing down all the time. So that could help you figure out a little bit, you know, where you are. But again, this graph is honestly not helpful to verify any of the solutions. Now, what's the deal now? So we have that. Okay, cool. But the second part is the x-coordinate, only the x-coordinate. However, this slope is for y over x, right? If we go back to the plot, it's kind of this thing. So it will tell us what's the next position of y in terms of x, but not the next position of x in terms of time. So that's why I find this very confusing. So the second part, what you need to do is the following. Basically, it is the initial position, and you have the derivative, right? You have the derivative here. So plus the integral from 0 to 1 of the derivative of that function, dt. So basically, that's all. So if we want, we can write it. Remember that the wording said that this was 1 at the beginning of the problem. So 1 plus 0 to 1, and then this thingy here. And, well, we will approximate that in Desmos. So here we have to write that. So it is 1 plus, and then the integral. I prefer, honestly, to do this. And then 0 to 1, 0 to 1. It is 0 to 1, right? Yes, because later on will be pi. So we have to be careful with these details. Then e, and then the power of cosine of t. And then dt we have to get down here, and then dt. and it's 3.34. Okay, 3.34, and then if you round up, it will be 16, so 2. Okay, there are no units, so perfect. That's it. Now here I would like to add something for those who are, A++, and it is the following. So what if we would have tried to use some kind of line tangent to solve for this problem? Well, what you could have said, so this is optional, and be careful with this. This is not the accepted solution. Okay, not the accepted solution. But let's see what we can do. So x of 1 is going to be approximately x of 0 plus the slope of x. So be careful because it's not the slope of y. So let's say, it's dx divided by dt at x equal to 0, and then 1 minus 0. And this is 1 plus dx dt. Remember, it was this thing, so cosine of 0 multiplied by 1. So it's approximately 1 plus e. And this is 2.7128, so this is 3.7128. Now notice that the value is greater, so it was an overestimate, right? Overestimate. How can we know that? Well, why don't we do the following? Let's compute the acceleration. Remember, the acceleration x was minus 1.44 at t equal to 1. But we would like to know the acceleration at t equal to 0, right? That's the right thing to do. But the acceleration was, let's see, we had it here at the beginning. So it's going to be e to the power of cosine of t and then sine of t. So we have that this is 0. So in this case, it does not let us know exactly what's going on, if it's going to be an overestimate or an underestimate. We will need to go to a higher derivative, like the third derivative. But knowing that at t equal to 1 is negative, it means that our function, is concave down. So when you estimate something with a line, you are always overestimating. So we confirm on that. That's optional. It's pretty cool. Also, it gives 0. So that in this case, we will need to go to a higher degree. That's at 0, but not at t equal to 1. Okay. So that with t equal to 1, you can also solve the problem. Probably in class, you have also always look at this because you are approximating a fraction from 0. But anyway, since you are approximating, you could also look at what happens at the end, not only at the beginning or in between. So, yep, great. This is optional. And then find the total distance. So, well, the total distance is going to be the integral, but be careful with the limits, between 0 and pi of the speed function, right? So the speed function, that this one. And indeed, right here, an absolute value to make sure that they know that you understand that. But remember that this was all that expression with the squares, blah, 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 blah. We have in decimals. So now we can make use of our super function and say, hey, I want the integral between 0 and pi. We have pi here down. Of what? Of our f of t, which is the speed, f of t. Okay. And we know that this should be positive because, so it's 1.32. But let's double check, right? This is going to be 1.322, nothing special, no units. The 3-digit rule after the period. And also always double check that it was in radians. Yes. So what if we add here an absolute value? Okay, let's do that. You have it here down. But then you have to put it here, not where it suggests. And we have 2.12. Okay, so we have to double check here that this function, the square root of let's see that we have all the squares, properly, 2 cosine square. Oh, look at that. So we have minus 1.5. That's not what we want, right? We want to remove this 1.5. So now we have this 6. So this is, let's remove that. This is indeed 6.03, and this is a good way to see how you can spot an issue in what you're doing. And then let's remove now the absolute value. It should be the same thing, and you get the same thing. Yes. So remember that because you don't have enough room here in decimals on the screen, your equation may be cropped, and if it gets cropped, you may forget some of these things. So that's a good check, to see that the absolute value here was the same without the absolute value because we have the square root defined by us, and that's always positive. Okay, so that's a great double check to be super A++. Okay, thank you so much. See you in the next one.